In the late 1950s and early 1960s, NASA stood at the edge of a new reality. Reaching orbit had already been achieved, and the moon was no longer a distant dream, but an active objective. Yet beneath the public excitement, engineers inside NASA were facing a quiet but serious problem. Chemical rockets, powerful as they were, had fundamental limits. They burned fuel extremely fast, required massive launch vehicles, and made long-duration missions inefficient and risky. Every additional kilogram of payload demanded even more fuel, which in turn required even larger rockets. This compounding problem made missions beyond the moon, especially human missions to Mars, seem technically possible but operationally impractical. NASA engineers understood that deep space travel would require something radically different. Shorter travel times were essential, not just for mission efficiency, but for crew safety. The longer astronauts spent in deep space, the greater their exposure to radiation, microgravity, and system failures. Chemical propulsion could not easily solve these problems. The physics simply would not allow it. At the same time, nuclear energy was already proving itself on Earth. Nuclear reactors powered submarines for years without refueling and generated enormous amounts of heat from relatively small amounts of fuel. To many engineers, the conclusion was obvious. If nuclear heat could be harnessed safely in space, it could change everything about space travel. This was not a reckless idea driven by imagination. It was a practical engineering response to a real limitation. The question was no longer whether nuclear propulsion could work in theory, but whether it could be controlled, tested, and trusted for actual space missions. That question would lead directly to one of the most ambitious propulsion programs NASA ever attempted. Stage 2, what Project Nerva actually was. Project Nerva began in 1959 as a joint effort between NASA and the U.S. Atomic Energy Commission. Its full name, Nuclear Engine for Rocket Vehicle Application, reflected its purpose clearly. This was not a research experiment meant to sit in a laboratory. It was designed to produce a real engine for real missions. At its core, Nerva was a nuclear thermal rocket. Unlike chemical rockets, which rely on combustion, Nerva used a nuclear reactor as a heat source. The reactor did not explode. It did not detonate. It simply generated intense heat in a controlled environment. Liquid hydrogen was pumped through the reactor core, where it was heated to extremely high temperatures. As the hydrogen expanded, it was expelled through a nozzle, producing thrust. The brilliance of this design lay in its simplicity. The nuclear reactor never touched the exhaust directly in a destructive way. It only transferred heat. This allowed the rocket to achieve exhaust velocities far higher than chemical engines could manage. In practical terms, this meant nearly double the efficiency, measured as specific impulse, compared to the best chemical rockets of the time. Safety was a central concern from the beginning. The reactor was designed to remain subcritical during launch, meaning no nuclear reaction could occur until the engine reached space. Even in the event of a launch failure, the reactor would not explode or spread radioactive material in the way the public often feared. These were deliberate, conservative engineering choices made to ensure that Nerva could realistically be approved for flight. By the early 1960s, Project Nerva had moved beyond design studies. Hardware was being built. Materials were tested under extreme temperatures. Entire facilities were constructed to support full-scale engine testing. This was no longer a speculative idea. It was a program moving steadily toward operational reality. Stage 3, the tests that proved it. Work to prove Nerva could function as intended, NASA established extensive test operations in the Nevada desert. The location was chosen for isolation, safety, and control. Here, full-scale nuclear rocket engines were assembled and fired under real operating conditions. These were not brief demonstrations or limited power runs. The engines were brought to full power and held there for extended periods. The results were remarkable. The reactors remained stable. Fuel elements held up under intense heat. Thrust levels matched predictions. Some engines were restarted multiple times, demonstrating reliability rather than one-time success. In several cases, engines operated longer than a real mission would have required, proving that endurance was not a limiting factor. Engineers carefully monitored radiation levels, structural integrity, and thermal behavior. The data consistently confirmed that nuclear thermal propulsion was not only viable, but robust. By the late 1960s, Project Nerva had achieved something rare in aerospace development. It had crossed the boundary from experimental technology to flight-ready hardware. Engineers had confidence not just in the engine itself, but in how it could be integrated into spacecraft. Studies showed Nerva mounted far from crew modules, with propellant tanks providing natural radiation shielding. Mission architectures were developed for Mars expeditions and heavy cargo transport. In every technical sense that mattered, Nerva was ready. This success placed Nerva in a unique position in space history. Many ambitious programs fail during testing. Others never leave the drawing board. Nerva did neither. It worked repeatedly, under the harshest conditions engineers could create on Earth. Stage 4. Why a working engine was abandoned. Despite its technical success, Project Nerva faced a challenge that engineering alone could not overcome. The political and cultural environment of the United States was changing. The Apollo program had achieved its goal. Humans had walked on the moon, and public attention began to drift elsewhere. Space exploration no longer carried the same urgency it once had. At the same time, the Vietnam War demanded enormous financial resources, and NASA's budget began to shrink. Without a clear, approved mission that required nuclear propulsion, Nerva became vulnerable. Crewed Mars missions were discussed but never formally committed to. Without those missions, the engine appeared to some policymakers as a solution in search of a problem. Public perception also played a role. Nuclear technology, regardless of its peaceful application, became increasingly controversial. Fear often outweighed understanding, and political leaders became cautious. In the early 1970s, the decision was made to cancel Project Nerva. The reason was not failure. The engine had met its goals. It had proven its performance. The cancellation was a result of shifting priorities, reduced budgets, and the absence of political will. Engines were placed into storage. Documentation was archived. Engineers who had spent years solving unprecedented technical challenges watched their work come to an abrupt halt. This moment marked a turning point. For the first time, NASA deliberately stepped away from a propulsion technology that offered a clear path beyond Earth orbit, not because it was impossible, but because it was inconvenient. Stage 5. What Nerva means today. Project Nerva remains one of the most instructive stories in space history. It demonstrates that technological progress does not move forward automatically. Success does not guarantee adoption. Even when a solution exists, it can be abandoned if circumstances change. Decades later, modern nuclear propulsion concepts still rely heavily on Nerva's data. The tests conducted in the Nevada desert remain some of the most comprehensive nuclear rocket experiments ever performed. The challenges Nerva was designed to solve have not disappeared. Mars remains distant. Deep space missions remain slow and expensive. Human exploration beyond the moon continues to face the same limitations engineers identified more than half a century ago. In that sense, Nerva was not ahead of its time. It addressed problems that still exist today, using tools that were already proven. Project Nerva shows that history does not always reward readiness. Sometimes the future arrives early and is ignored. The nuclear rocket NASA built did not fail. It simply waited for a world that never came. Even today, the problems Project Nerva was designed to solve have not disappeared. Mars is still far away, and deep space travel is still slow and expensive. Astronauts remain exposed to radiation and long mission durations. The physics has not changed, only the calendar has. Modern space agencies now quietly return to nuclear propulsion studies, and when they do, they return to Nerva's data. Test results from the 1960s are still referenced today. Few space programs can claim that kind of legacy. No modern nuclear rocket has yet surpassed what Nerva already demonstrated, not in efficiency, not in endurance, not in real-world testing. Project Nerva proves that progress is not always about invention. Sometimes it is about remembering what was already achieved. The future of deep space travel may not require new ideas, only the courage to revive an old one.